Okay, so let's start. So welcome everyone to the 1W-MINDS seminar today. So 1W-MINDS seminar has enjoyed great success in the past few months by bringing many wonderful talks to everyone in this very special year. And also today's talk is very special since it's actually the first inaugural seminar for the second time zone, more friendly to Europe, Asia, and Oceania. So now it's my great pleasure to introduce Professor Wang from Hong Kong University of Science and Technology. So Professor Wang is currently the Vice President for Institutional Advancement, Chair Professor at the Department of Mathematics, Director of HKUST, the Big Data for Biointelligence Lab. So Professor Wang has done many influential works in computational harmonic analysis, such as wavelets and frames, mathematics of signal processing, data analysis, and machine learning. He also serves as an associate editor for several journals, including Applied and Computational Harmonic Analysis. So today he will give a talk on improving generative adversarial networks using VGrow. So let me now give the stage to Professor Wang.
Yeah, thank you. It's a great pleasure to kick off this meeting. I know, I complained to Mark that I have not been able to join any of the meetings because of the time zone difference. I actually suggest we move to my evening time, like 10 p.m. or something. But because of California concern, the California situation, it will be difficult to make it work for everybody. So I'm really glad that we now have a second seminar series, and glad to see so many friends here. Okay, so without further wasting time, let me just begin my presentation. So I'll do the screen sharing. Let me go to the, oops, let me do this. And let me do the full screen. Okay, so you can see the talk, the title of this. Basically, I'll give a very a fairly detailed introduction to GAN. Okay, so generative adversarial networks, and then the last few maybe last 20 minutes or so, I will talk about our own work. Okay, so so let me actually begin by with this particular slide. And many of you would recall that this was in 2018, a portrait. This was a portrait on the, here, was sold for over $400,000 US. Okay, so this was the essentially a portrait generated by AI. Okay, so how did how did the artist, or I shouldn't say artist, how did they generate this this portrait? Actually, it's kind of interesting to see the signature on this portrait. You could clearly see the signature. Okay, so you blow it up, it looks like this. Okay, this was this formula here, which I'll get to eventually. So what does it mean? Okay, so this actually is exactly when the first GAN network was designed. This was the target function. Okay, that's been used. Okay, so I'll explain a little later. Okay, so since then, of course, let me see. I don't know why. Hold on. Let me see. I may have a little bit of a problem. I may have missed 2 slides. So just quickly, sorry, just bear with me. I want to see what I thought I have 2 slides that may be a little bit missing. Okay. Okay. I see. This. Okay, so yeah, okay, that's good. That's good. So I found out what's going on. So now let me go back to the, sharing. Sorry for the hiccup here. Actually, I only missed one slides. Hold on. Okay, so so this is actually a piece of music generated by AI. I'm gonna skip the first 1.5 minutes. Let me just go directly to oh. Okay, it's actually pretty impressive. I think I may have I should have shared the sound from the share screen. I forgot to click that, but you could get a little bit of idea what kind of music you can do with AI. Even though I think this one is not entirely AI generated, the some parts were actually humanly generated. Okay, but it's still very, very impressive. Actually, we showed this to some professional musicians. They were actually blown away, and they also don't believe everything was done by a machine. I'm not going to second guess. Okay, so we do have a team here that experimented generating music from AI. I would say it's pretty good, but not nearly as good as this one. Okay, of course, we don't have a professional team to handle this kind of thing. So anyway, I'll leave that to you guys to figure out exactly what was going on. But there is one thing I don't think there's any question. AI music will eventually come. Okay. So this is another example, again using GAN. So we were able to, take some of the portraits, art portraits, and generate some of our own from GAN. Okay, not spectacular, but certainly some of them look quite interesting. Okay, and this is a very well known. I mean, if you look at all these faces, okay, they're actually not real people. They're completely generated by AI using GAN. Okay, this is the technology today for generating faces, human faces, is actually very mature. Okay, so this is, I believe, the best ones are done by a team in NVIDIA. So you can generate very high resolution faces, human faces, and just look completely indistinguishable from real faces. Okay. Okay, so what are we talking about? So we call it GAN. So I'm just Generative Adversarial Nets. This is the first. This is a groundbreaking work by Ian Goodfellow in a paper in 2014. Okay, a bunch of authors, but the lead author was Ian Goodfellow. And it was really trying to address the following question, given a set of data, let's say you have a bunch of dog, or human faces, or some paintings like Van Gogh paintings, okay? Can you generate something very similar in style, okay? Now, we're not talking about something that you take existing Van Gogh, do some perturbation or something. We're not talking about that. We are really talking about, you want to generate either a human face that absolutely look like a human face, but it's not a real human face, okay? Or a painting that experts may even think is a Van Gogh painting, but actually it's not, okay? So in some way, this is how we measure similarity. So I will get to that a little bit later on. So here are two, typical data sets. One is, MNIST, we all know, and this is a data set of dogs. Okay, so you take these data sets. For instance, let's say just take the second one. These are a bunch of puppies. Okay, and you want to generate new puppy faces, okay, that are not really one of those already in the database, but something completely new. But everyone looking at it would say, oh, this is a puppy. Okay, so something like this. Okay, now so what was the idea? The idea was in the original paper, which I call the Vanilla GAN, okay, because since then GAN has made a significant progress, has has undergone a lot of more developments. Uses two neural networks to compete against each other, which I'll get to a bit later on. Okay, and as I mentioned, this is really a very interesting idea. So Yang LeCun actually called this the best, or I should say, the most interesting idea in the last 10 years in machine learning, in my opinion. Okay. So, so how did how did the Ian Goodfellow team do this? And what are the mathematical principles behind this? Okay, so this is what I'm going to talk about today. Okay, so what is the basic idea? Okay. Now, the basic idea is very simple. You're given a training set X. Okay, the set can be just the ones I just displayed. For instance, it can be the second one, this puppy faces. Okay, now we want to generate samples that look like puppy faces. So how do we do this? Okay, so mathematically we assume X comes from an unknown distribution. Okay, so we have a distribution which here we denote by P sub X, and we try to approximate this distribution. So if we know exactly what this distribution is, we can just take samples. Okay, if we take samples, then obviously we got a lot of puppy faces. Okay, and or Van Gogh paintings. So this is the idea. Of course, we do not know the distribution. Okay, so this is the underlying assumption, and we try to learn this distribution. So that's the idea. Okay. Now, how do you learn a distribution? Only from samples. Okay, you don't have a formula, you don't have an analytic expression of P sub X, you just have samples drawn from this distribution. How do you learn it? Okay, so if we could somehow learn this distribution, then we would be able to generate samples that just look just like the one in the training set. Okay, that's the idea. So in the original, in the Vanilla GAN paper, okay, the idea is, let us start off with a random noise. In that case, it will be independent Gaussian. Okay, depending here, I is identity in the ambient dimension is the same dimension as whatever you're given. In the case of MNIST, it will be 28 by 28. Okay, and of course, when you do this random noise, it's not going to give you very good results at all. Okay, so your idea is to find a nonlinear function called the generator function G. Okay, so this G will be what we call the generator. Okay, so such that when you passes this random noise through G, this new random variable has a distribution that approximates the distribution you want to find. Okay, in other words, you're really looking for this G, so that G of Z mimics the distribution of your training set. Okay. Okay, so how do you find it? Okay, of course, once you find such a G, then any random sample from this is 0i. Okay, so from Gaussian, this Z should be N0i, just as before. Will give you a sample through G that looks like the sample CX. Okay, this is the whole idea of GAN. Okay. Now, here, even though we talk about neural network, we actually don't get into details of neural network. So what kind of role does neural network play here? Okay, so the only role it plays is that it can be used to approximate any function. Okay, so think about polynomials if you are not comfortable with neural networks. So we don't talk any detail about neural networks. Okay, think about G, even though it's in the form of neural network, to be a function that can be polynomials, for instance, with a lot of parameters. Okay, so neural networks would have a gazillion parameters, and we have there are several results, including by people in this audience who have shown that it can be used to approximate any function. Okay, so this is the only reason we actually use neural network, because it's a great approximator of functions. Okay, so since we know nothing about G, let's just model it as a neural network with parameters, and then we fine-tune the parameters. Okay, but here, in the traditional, when we first did a lot of these neural networks, we were using neural networks to discriminate, to classify things. Okay, so whether this is a Van Gogh painting or not a Van Gogh painting, or this is a puppy, not a cat, something like this. Okay, but here really the innovation is here is to use two neural networks sort of competing against each other, so that using this competition to improve the generator, and in fact also the discriminator, which I'll get to later on. Okay, now it turned out this whole thing can be done in the form of a minimax optimization problem. Okay, which we'll see in more detail. Okay, so here is the Vanilla GAN, and that's what Ian Goodfellow and his co-authors have done. Okay, so this is more or less the architecture of this whole thing. So before we get to this formula, let me just explain what was actually happening here. Okay, so what was happening is you can see you have training set. Think about these being puppy faces or just human faces or Van Gogh paintings. Okay, well, whatever you can think of. And this is a typical like convolutional neural network architecture here, and you input some random noise, as we already said. Okay, and this is your generator function, which is a neural network, and you send this random noise through the neural network, the generator. You come up with something. Okay, so this would be the fake human face or fake Van Gogh. Okay, it will generate, and you could see that in the beginning this is going to be terrible. Okay, so then you build a discriminator here. You send the fake images to the discriminator along with your training set. Okay, and of course in the beginning it's really bad, right? So it's very easy for the discriminator to tell this is fake, this is real. Okay, so the training set is real, and whatever you generate is fake. Okay, and then you send this back saying, no, this is what you have done is not good enough. Okay, through this process, you gradually improve the generator using stochastic gradient descent, and eventually it got to the point that you cannot tell the two are different, and then you will consider that the generator has done its job, okay, and because it successfully fooled the discriminator, okay. So that's how this whole process works, okay. Now, why? So mathematically, what do you do? Okay, so so in the model, in the vanilla GAN model, you create something. We say the discriminator. Discriminator is simply a function d, which is also modeled using neural network. So on the right hand side, you have neural network, which is your discriminator. So the discriminator does the following: it tries to give a very high value to data from the training set, to your true distribution, right? To your training set here. And it also tries to give a low value to the ones you generated. So this is what a discriminator does, right? Assigning high probability. So think about D being a probability. It's in between 0 and 1. You assign high probability to training training samples, and low probability to the fake ones. Okay, so this is why we try to maximize. We try to find the discriminator that maximize the part that coming from the training sample. You can see X coming from the true distribution, sample distribution. And also maximize this means you minimize D of G of Z, okay? Means then you try to minimize the probability of the generated images. Okay, so this is what you try to do for the discriminator. You try to build as good a discriminator as you can to tell apart the real sample from the fake ones. Okay, but on the outside, you also try to improve your generator so that you minimize this whole thing. Okay, in other words, you want to make sure this second term, the first term doesn't depend on G, okay? You try to make sure the second term is as small as possible. That means the value of G of the generated samples for the discriminator is as large as you can get. Okay, that just means it passes the discriminator. So this is the whole setup. That's why we're talking about the minimax problem. We have this right-hand side is exactly, this is exactly the signature of that portrait being sold. Okay, so this is the vanilla GAN. And it actually was very effective in some for some training sets. Okay, and of course there are also problems which I'll get into. Okay, all right. So the next question is we have set up the problem here. Forget about this neural network. This is purely an architecture problem. How do you design the neural network to make it more effective? Okay, so this is not the point of this lecture today. So the next question is.
Can I ask a quick question? The training set that you use to train the discriminator, is it the same that you use to generate the generator, or is it just
it's the same. It's the same, but the generator you see doesn't know the training set, right? The generator only input the noise, and at no time it actually has directly uses the training set. It just input the random noise, but because it cannot do a good job, so the discriminator tells the generator saying, this is lousy, you got to retry it.
But the generator is also trained using images, right?
Well, it's exactly. It's trained through when you go back to the discriminator, it tells you it's no good, then you have to improve. Then of course it uses the training set to improve it.
Thank you.
Yeah, it doesn't directly train on the it's not trained directly on the training set. It's trained in the feedback loop when you do this.
Okay, thank you.
Yeah. So basically, I mean, for these kind of minimization, minimax problem, you do a alternate, projection basically. So the first one is you just say you're already given the generator, and then you optimize the discriminator D using using stochastic gradient descent on samples. So I will get to this a little later on, because these are expectations. Okay, with expectations, we don't have explicit formula for P of X, P sub X, and we also don't have analytic formula for both the neural network or both these functions. So we approximate these expectations using sample averages on mini batches. Okay, so we'll get to this later, but this is not the most important thing. You just realize that you can approximate these expectations using sample averages. Okay, so once you train the discriminator a little bit, you improved it, you go back to the generator. You say, okay, I'm going to minimize, given a generator, minimize G. Okay, also using stochastic gradient descent. Okay, in fact, the first term does not depend on G, so it's really just a second term here. Okay, just second term. This is a very standard alternate projection. Okay, so many problems. Most of you are familiar with this. Okay, but this is an interesting part in his paper, in the Vanilla GAN paper. It says actually this second part sometimes is not effective. So we actually replace it by something, forget about this log 1 minus D. It just replace with minus log D of GZ. This is called, in his paper, it's called the log D trick. Okay, they claim this log D trick actually works better in many situations, but they don't have they don't have a framework for why this actually works. Okay, and I'll get to that later on. Okay. Okay, so this is the Vanilla GAN. Okay, and so now let's try to be a little bit more general. Okay, so we know we have a distribution. We don't know exactly what it is, but we want to approximate. So this target distribution is, as I say, is a P of X, and we try to find the distribution Q of G. Okay, G where this is formed by taking a Gaussian and going through a function G, which is a neural network, of course. Okay, so we want to basically, this is what we try to do. We find G so that this distribution Q sub G is very similar or very approximates P sub X. Okay, so from this point of view, mathematically, we may want to know what do we mean by the two, one distribution approximate another. Okay, that's one of the main important questions. You want to approximate, you have to know what do you mean by you want to approximate. Okay, so you need to find a way to quantify how close. In other words, you need a metric. Okay, well, it turned out in probability, this is actually a fairly classical area. You can measure the difference between two probability distributions. Here, I'm just for simplicity, I'll assume there are density functions, P and Q. Okay, you can measure them by something called a divergence. Okay, so the most commonly used is a KL divergence. It's a Kullback-Leibler divergence. Okay, so we generally call them KL divergence, and this is written in this notation. Okay, it's really just the expectation of over basically over the distribution P of log P over Q. This is a really unintuitive way, unintuitive sort of divergence measure. Why does it work? Okay, and in fact, it's pretty easy to show this is some kind of distance. Okay, and the other one is called the Jensen-Shannon divergence, which is more symmetrical. If you look at KL, it's not symmetric. KLPQ is not equal to KLQP. Okay. However, for Jensen-Shannon, it's totally symmetric because M is half the average of the two. By the way, there's a typo here. This KL, not KS. I made a mistake here. Okay. So, so these are the two fairly commonly used divergences. Okay, but it turned out there are other divergences one can use. Okay, and there's a very broad class of divergences, and I'll get to this later on. So the interesting thing is, it turned out for the if you look at the Jensen-Shannon divergence here, actually the vanilla GAN turns out to be exactly equivalent to the min-max of the Jensen-Shannon, to be the minimization of Jensen-Shannon divergence. Okay, so this complicated the minimax problem, well, at least looks complicated, even though it's quite simple. You can mathematically show that it is equivalent to this minimization problem, the minimization of the Jensen-Shannon divergence. Okay, so this is really quite interesting. So naturally, you may ask, well, can I replace the Jensen-Shannon divergence with KL? And the answer, as you will see, is yes, you can. In fact, there are other kind of divergences. Okay, the only problem, we use Jensen-Shannon is we have this dual form. I call the minimization of the divergence the primal form. Okay, the primal form, and I call the above the dual form. Okay, and it is actually a dual form, as I'll explain a little later on. Okay, so the primal form looks very simple and is also very intuitive, but how do you compute it? Without actually knowing what is PX, P sub X explicitly, and with all the neural networks involved. Okay, how do you actually evaluate it? It doesn't seem to have a good way to do this. That's why we actually converted into the dual form, so we could actually use sample averages to approximate this. Okay, so this is really the beauty of these dual form. Okay. Otherwise, it will be a highly non-trivial problem to do. Okay. And as I mentioned earlier, with expectations, if you can convert anything to expectations, we have a way to find it. Namely, we just estimated using these sample averages. I mean, this is just law of large numbers. This is how we do it anyway. And we don't do it for all because it would be too slow. We use a mini batch. Okay, we fix a mini batch size and just do this. Okay. So this is all these are fairly standard of course, in machine learning. Okay.
So sorry, there is a question on chat, request for clarification. Someone is asking whether this equivalence holds under the log D trick.
No, it doesn't. Yes, I will get to that too. It's actually, this is the thing, it does not work for log D. This is purely Jensen-Shannon and the vanilla GAN. Okay, no log D trick. Yeah. Okay, so actually, the GAN, the theory is very good, and the people got excited. So people started training different things, and they soon realized it's actually difficult to train a GAN. In fact, there is a paper. Just the title is "Why It Is So Hard to Train GANs." Okay, so you could see. Let's take P to be the standard Gaussian. Okay, to be the standard Gaussian, and if you take another Gaussian, you shift it a little bit. And you could see if you look at the Jensen-Shannon divergence, you could see there is almost the gradient is essentially zero. For Q to be too far away from P, which is understandable. In fact, this problem even today is not resolved. It's very hard to, if you start off with P like this, and you if your target is P like this, and you start out with Q like this, it will be very difficult to get it to converge to P without doing something that's a little bit unusual. Okay, so this is the vanishing gradient problem, which actually happens quite often. Okay, this is one problem. There is another problem which is also very common. It's called the mode collapse. Okay, so you're stuck in a local minima basically. So then it does not generate a variety of your generator is stuck in some kind of local minima circle where cycle in which it keeps repeating the thing with very little diversity. You can see this is some, this is one time you stuck the puppy face got stuck in a mode collapse mode in this mode, and you could see that there's not a whole lot of diversity being generated and just stop the convergence. Okay, so this kind of problem occur quite often. Okay, and so which I'll come back a little bit later on. Okay, so now I want to go to a slight generalization of the Jensen-Shannon diversity or the KL diversity. Actually, this has been studied in the 60s, maybe early 70s. Yeah. So we already understood there is something called f-Divergence. Okay. So besides Jensen, Shannon, and KL, and Jeffries and everything, you could just take any convex function. So it has to be strictly convex. Okay. With the property that f1 is equal to 0. Okay. Now I added condition. This is essential because sometimes you have singular, you actually need this condition. But anyway, let's not worry about this more technical. The original standard definition is you take any strictly convex function with f1 equal to 0. Okay. So what is the f-Divergence? F-Divergence is just like the KL divergence, where you just do this. Okay, so you take the expectation with respect to P. Okay, and then you do f qx over P of x. So this is what you get. Okay, it's a standard definition. But why is the divergence? I mean, this how does it work? Well, you can use the Jensen's inequality because f is strictly convex. Okay, so this integral here is strictly, well, it's not strictly, it's greater than or equal to this. You can move the, you can exchange f with the expectation with the, but you get an inequality. Okay, and of course this one can be written like this, and equal to f1 equal to 0. And equality only happens when q is equal to p, basically, or q over p is linear. Okay, but this, we know this isn't linear. Okay, so because there are distributions. So basically, you get strict inequality if q is not equal to p. That's why it's a divergence. Okay, it measures sort of the distance. Okay, all right. So that means we have numerous f you could use. So naturally, one would ask, well, given some of the problem we encounter with Jensen-Shannon, maybe we could try some other f. Okay, and now, or we can develop even a more general theory just for f divergence. Okay, and that has been done. And here is a list of f divergence with a different f. So KL we already know, Jensen-Shannon we already know. There's something called Jeffries. This is also known. And we actually figure out there are several that correspond to log D. And this is one of them. Okay, so the log D trick also corresponds to some f. This is one of them. Okay, in fact, there's another one that's even better. In fact, it corresponds exactly to the log D trick. Okay, but I'll list this one because we implement this one. in our experiment. Okay, so now the general problem for what we call f-GAN. F-GAN just simply means, we use f-Divergence minimization for GAN. Okay, so you can take any strictly convex function, and you change the Jensen-Shannon to f-GAN. You try to minimize this. Okay, and so now we have a problem because we know these primal problems are very difficult to do. Okay, so the question is, well, is there a dual form we can do to actually compute it? Okay, so it turned out you can do that. This was this was actually stated in one of those papers by Nguyen. In fact, the Berkeley group, Michael Jordan was also one of the co-authors of the paper. So you could use something called a convex dual to convert this primal problem into a very similar dual problem that uses expectation. So you can use sample averages to approximate these. So the discriminator T here, D there is now being written as T, and it's no longer called a discriminator, it's called a critic. Okay, we call this a critic function. Okay, so kind of like a discriminator, but it's we call it critic. Okay, and here you have to go to the convex dual of f, which I will not go into detail. You can, it's called a Fenchel dual also, okay, or Legendre-Fenchel dual. It's a fairly well-known subject. Okay, and with the dual version, of course, now we can do exactly the same thing for as we do for the for the vanilla GAN. Okay, and again, as I mentioned, we measure both the critic function, which was the discriminator in the vanilla GAN, and the generator using neural networks. And once we do that, we write them in the form of parameters. Okay, so we have the fixed architecture, but we have a bunch of parameters need to be tuned. So we just denote them by parameters, theta and omega. Okay. And the parameters are optimized by stochastic gradient descent. Okay, this is exactly the same way this is done, and the effect was pretty good. Although you can, I mean, for certain f, it behaves better than other f's. Okay, so certainly there are f like the log D trig would do better than the vanilla GAN. Okay, but still, it has a lot of instability as well, like a mode collapse, for instance. Okay, it runs into almost the same problem as the vanilla GAN. So we were also thinking about this this problem. Okay, so we certainly tried from the dual model. Okay, and try different f and try different ways to improve the training. Okay, what we discovered, as I stated here, is we got the same problem. Okay, we often run into the same problems. But then it occurred to us that there is actually a way to directly solve the primal optimization problem. Okay, this was this was very at the time was we were also surprised. Okay, so it turned out by doing that, you actually get better results. The stability problem is much more stable in terms of training. You still, from time to time, running into the gradient, vanishing gradient problem. Right? That you, as long as you use the same idea of minimizing divergence, you cannot avoid that problem. Okay, but it does seem to be more stable. We have fewer mode collapse problem. Okay. And so how do we do this? In fact, one question, how do you actually minimize the primal problem? Okay, so we called our method the VGrow, Variational Gradient Flow. Okay, so how did we do this? Okay, so the way so the idea is to use a variational gradient, or we call it functional gradient, if you call. So here's the idea. Okay, so let's say you want to minimize this regression problem. Typical regression problem. You have some value yi. You want to fit a function, which might be a neural network or something else. In terms of basically you want to do this. Okay, so so the gradient boosts the trees. Okay, so basically you, instead of you may have a parameter in general, but instead of the parameter, you could also take the functional gradient, okay, so, or variational gradient, treating f as a function, and just do the variational gradient. And once you do that, you update. So you do this. This is like a typical gradient descent. Okay, we update along the gradient direction to find the optimal f. So for, let's say you already have the m step, the next step would be you take the m step, adding the functional gradient. In other words, you add the gradient or the negative of the functional gradient with respect to f. Okay, so this is how you do it. And you have a step size s. In many cases, it just takes up to be 1. Okay, so then you do this. You get a you increasingly you get better approximation. Okay, so this is a well-known technique. Okay, and so we actually, it turned out we could directly solve this using this variational gradient, basically. Okay, and so basically, so idea is that we first find the variational gradient with respect to q theta, okay, just as we did for the regression problem. Then we just do exactly the same thing. We update this. Let's say we update our generator to a new generator after moving along the negative gradient direction with a step size s. Okay, so we've done that. But the next step is we update theta. Once we have g of n, we actually update the parameter theta so that the neural network with parameter theta would best approximate this this g, the gn bar. Okay, so we don't update theta n directly. Okay, we actually update the g of the generator function first. Then we try to fit the parameter theta. So instead of directly updating the parameter, okay, it turned out this worked out really well. Okay. Okay. So so the key, as I said, is this whole thing can be approximated. In fact, we can use sample averages and some kind of related to logistic regression to actually compute this. Okay, to approximate. I wouldn't say compute this, all approximation, right? So this looks still fairly theoretical, and we have no way of doing this. But it turned out we can use. There is a way to approximate all these using sample averages. I'm gonna I omit the details, but you can find in our paper. Okay. So this is why I call we call this a primal optimization, minimization problem. Okay, algorithm. Even though I think to be honest, it probably should be semi-primal, because for this part, okay, we still need to use sample average. We have to convert this part into some kind of, not necessarily, I wouldn't call it dual problem, but it's similar. Okay, so for at least for this one part, we need to use a dual version, or at least some sort of dual version. So maybe more honestly should be called semi-primal optimization algorithm. Okay, and the other thing is if we go back to this step, we say after we update the generator, we update the parameter. Okay, but actually we don't do that. In practice, we found it's not necessary and too slow. So what we do is we do several, just like the gradient boosted trees. We actually do several variational gradient update with small step size. Then we do the after we do a few, we do the we update the parameter. Okay. So here is a picture. You know, we start off with something, then we do the variational gradient flow. We do a few times. Then after a few steps, we say, okay, enough. Let's update the parameter. So we update the parameter to theta 1. Then we do a few, and then we say, okay, enough. Let's update the parameter. So this is turned out to be faster. Okay. The other one also works, but it's computationally is a bit is slow and unnecessary. Okay. All right, so this is an example. So we have a target distribution here. Okay, you can see on the last image is the distribution, you know, our target distribution. And we start off with a Gaussian. I mean, you can see it's almost like a dot because it's the scale. This is a scale problem. Okay, so we just perform. You know, you do the variational gradient, and you can see this whole thing. The G will pushes everything. You know, you can see the arrow here. Okay, they'll point this direction, that direction, and the things. So now you get something like this, and then you update the parameters. And then you compute the variational gradient again, and that gives you all these arrows where you're pushing this whole thing. And you get something like this, and you do exactly the same thing. And at some point, you realize you push a bit too far, so you have to come back, okay? And you get, you know, these are the things. So these are the steps in getting closer and closer. In the end, you know, after the last one, this is what you get, okay? So it's actually worked out really well. But this is a fairly good illustration of what is happening. Okay, so we put this to test. It turned out on MNIST, this is a fairly commonly used data type. There is almost no difference between any of the methods. I mean, it's very stable. You know, Vanilla GAN, with or without log D, KL, log D, or Jeffrey, they're all the same. They give you very much the same result. Okay, and for the Fashion-MNIST, you have these are the generated images. You get this real samples, and we perform on this. Okay, so we use the FID score for the, you know, this is a fairly standard, and the lower the better. Okay, so you can see they're all also actually quite close, even though the gap here is pretty big. This you know, some just don't perform well. I think the Jeffrey, usually we found the Jeffrey the Jeffrey divergence doesn't seem to work that well, but both KL and log D consistently give the best performances. Okay, so for CIFAR-10 is a more difficult data set. So you can see these are generated samples. Okay, so you can see, I mean, this is the blow up of the score. Okay, you could see that the gap actually is quite significant. Okay, so even though, because the scale is very, very high, so you don't see, but in effect, definitely the log D and the KL performed really well in using our VGrow. Okay, so the Vanilla GAN here has a little bit of gap, and the Jeffrey is, as I said, it doesn't matter what you do with it, it just doesn't perform very well. So not all the f-divergence are the same. Okay, some definitely perform better than the other. Okay, and we have very similar result. This is the celebrity data set, and we were using VGrow. We were able to generate fairly good samples. You could see, okay, very stable, and this is the comparison of score. Okay. There's another one, real sample, the church samples, and these are the generated samples from our using the VGrow. Okay. By the way, this is actually a very difficult data set to work. Often you do run into these instability problem. Okay, for VGrow we didn't run into. We actually handled pretty well. Okay. So we also tried these enemy generation. Actually looks pretty good. In fact, we have people working in this area. They thought the one we generated, some of them are not good. Like this one, I don't think it's very good. But some of them they feel it's actually good. They could even use it. So one of the interesting techniques is called a progressive training. It's called a v-GAN. This is by these high resolution facial images were generated using v-GAN, the best quality ones. But originated, I guess, the first developed by this team from NVIDIA. Okay, now they since updated a little bit, so it's really good. Especially for face generation. Okay, you can get high resolution, let's say 1024 by 1024. Okay? Very high resolution images, excellent quality. Okay, so you can implement exactly the same technique for VGrow. Okay, and then we are able to generate a bunch of good looking. Actually, these are what we were able to generate. They look actually pretty nice. Okay. Of course, sometimes we throw away a few that don't look very nice. You can see like here, this one doesn't look like, and this one clearly has some problem. But there are many that looks actually very nice. Okay. And these are the ones we were able to generate using the progressive training. Okay. To just get to the summary part, we actually developed a general framework for using this so-called variational gradient flow, or VGrow, probability space for GAN. Okay? And the distribute, the optimization process is a bit complicated, but it's actually pretty easy to implement. As I already mentioned, there are some details I omitted. Okay, it's also related to the Fokker-Planck equation. Okay, so when you write down the variational problem, you actually get something related to the Fokker-Planck equation. Okay, and it can be connected with other popular methods. Okay, so and we evaluate many the performance on different divergence. Basically, the conclusion we have is it offers better stability, and we definitely running into fewer mode collapse problem, for instance. Okay, so in general, the performance has been quite good. And from the FID score point of view, usually we got the best score. Okay, I don't have the table here. Okay, and there are some references for you to, if you're interested. This last paper, this paper appeared in ISMO in 2019. This is exactly about the VGrow I just talked about. And of course, these are the first three papers are well-known papers. Okay, so like this Ian Goodfellow paper. Okay, and the last one was a survey kind of paper I wrote called a mathematical introduction to GAN. Okay, and I didn't send it for in publication. I just posted on archive because I discovered, I mean, at least to me, a lot of these papers were written from a computer science point of view. You know, I want to give a people like us who are more mathematically oriented a chance to maybe an idea how does it work mathematically. Okay, so I wrote this paper. I didn't talk about the algorithms and just simply the mathematics. Okay, and I think I'll stop here. Thank you, and you know, I'll be happy to answer questions.
Okay, thanks, Professor Wang's talk. And there's actually a couple of questions from the chat.
Okay.
Yeah, this the first question that